Okay, so let's begin this video on the principle of inclusion-exclusion with an example. And in this example, we're asked to count the number of arrangements of the word burger that have the two R's beside each other in the arrangement, or that start with a vowel. So the word burger has two R's, and that's the only letter that's repeated here. So if you count, I'll label these conditions 1 and 2. So if you count the number of arrangements that satisfy the first condition, well, we know from a previous video that all you need to do here is to treat the two R's being beside each other as a single block or a single unit. And so really what you're doing here is to just count the number of arrangements of 5 distinct objects. So there are 5 factorial ways of doing so. In number 2, how many start with a vowel? Well, there are only 2 vowels in the word burger, U and E. So it's easy enough in this case to divide the second condition into 2 cases. Either we start with a U, in which case we have to rearrange the letters B, G, E, R, R in some manner, or we start with an E, in which case we rearrange B, G, U, R, R in some manner. And in both cases we know what the number is. Again, by a previous video here, this is a permutation of a multiset, right? Or a permutation where some elements are repeated. It's 5 factorial over 2 factorial for each one. And so for the second case here, we have 5 factorial ways, right? So first condition, there are 5 factorial arrangements satisfying that. Second condition, 5 factorial arrangements satisfying that. But now, think about what's being asked here. We're being asked to find the number of arrangements that fall into 1 or 2. And your first instinct might be, maybe we can just add them up. 5 factorial plus 5 factorial. And, well, this is going to be like 240. But really, if you think about it, this 5 factorial arrangements and this 5 factorial arrangements, they have elements in common. I can start my arrangement with a vowel, for instance, and have the 2 R's beside each other. And so this particular arrangement that I have here has been counted twice, right? We've overcounted. And so 240 here is actually more than what we need. So what do we do then? Well, we recognize that it is exactly these arrangements that we have to subtract once to get the correct answer, right? Why do we have to subtract them once? Well, because we counted it twice. So now we have to count how many arrangements have 2 R's beside each other and start with a vowel. And how many is that? Well, we can do the same thing as here on the left. It can either start with a U or an E. But now we're arranging B, G, E, and R, R as a single unit. Here we're rearranging B, G, U, and then R, R as a single unit. So there are simply 4 factorial ways of doing each one. And they combine and give you 2 times 4 factorial. Therefore, the final answer is not 240, but we subtract whatever it is that we counted 2 times. 2 times 4 factorial. And this is 240 minus 48. And this is now the number of arrangements that satisfy either 1 or 2 here, either condition. And what we just demonstrated there was called the principle of inclusion-exclusion. If you have two sets in a universe of items, and so say this is U, and you have A1 and A2 as two sets of objects, then the union of A1 and A2, its cardinality can be computed as follows. You count everything in A1, that's this one. Then you count everything in A2, that's this term. And then you recognize that everything in the intersection has been counted 2 times, right? One more than what you need. So you subtract 1 copy of the cardinality of the intersection. And this gives you the union. Now note that this is very similar to the sum rule, which says if you have a partition, then it suffices just to add the individual cardinalities up to get the union. Right? But remember, what does it mean if you have a partition? It means A intersection B is equal to the empty set. And this should now be apparent to you that this principle of inclusion-exclusion for two sets is basically the sum rule, right? But generalized to the case where you don't have a partition. Right? So when you don't have a partition and you've actually counted the intersection twice, then you remove it 1 time to make it accurately count the union. Now finally, by taking complements of all the sets here, you notice that we can also write this as a counting problem where you're counting how many ways are there to avoid the condition in A1 and the condition in A2. Right? So how many elements are in neither A1 or A2? And those are the elements out here. And so that's simply equal to the universe minus the union of A1 and A2. Right? So all the elements that are in neither of the sets, which then simplifies to be that statement that you see inside the box. Oops. So minus A1 minus A2 plus A1 intersect A2. And there is a more general statement for the principle of inclusion-exclusion for n sets, right? Not just 2. And how this works is, as an analogy to this avoidance of A1 and A2, right? Computing how many elements are there in neither of those sets. Now you're computing how many elements are there that belong to none of the sets A1 to AN. And so we just follow the same pattern that we saw on the previous page, where we start with a union and subtract all single sets, right? The cardinalities of all single sets taken one at a time. But, well, when you subtract A1 and you subtract A2, you've subtracted those objects in their intersection 2 times, right? Again, similar to the previous page. So you have to add them back, A1 intersect A2, and you have to add back all the pairwise intersections. Okay, so that's what this notation means here. For all I less than j, right, you take their intersection and subtract. Well, I mean and add, right? You're adding them back. Then you continue and you do the same for all triple intersections. And all quadruple intersections, now you're adding. And so on and so forth, until you get to the final term, which is just the intersection of all n sets. Right, so that it's going to look like the following. A1 intersection, A2 intersection, all the way to AN. with a -1 to the nth power. Right, so you're either subtracting the very last intersection or adding the very last intersection, depending on whether n is an odd number or an even number. So as the last example here, let's apply this to this example where we're computing how many integers in the set from 1 to 200 are not divisible by either 3, 13, or 23. So this is exactly the principle of inclusion-exclusion, right? We have 3 sets in that example that we're trying to avoid, right? We're counting the number of objects that are in none of these sets. If we define A1, or let me define it using the subscript A3 to be the set of integers in 1 to 200, divisible by 3. A23, well, 13 first, is the set of integers in the same set 1 to 200 divisible by 13. And then same for 23. Then what we are computing here is the cardinality of the intersections of the complements. Right, so I don't want anything in A3, I don't want anything in A13, and I don't want anything in A23. By the principle of inclusion-exclusion, this is equal to the universe minus these single sets plus pairwise intersections and finally minus the intersection of all 3 sets. And now it's quite easy to compute. U is just 200. Well, what's A3? How many integers in 1 to 200 are divisible by 3? Well, we can just divide 200 divided by 3, get the quotient, and take the floor function. And that gives you exactly how many integers are there in this set that are divisible by 3. Same for 13, same for 23. Okay, well, how about this one? A3 intersection A13. A3 intersection A13 is now the set of integers that are divisible by 3 and 13, which means these are exactly the set of integers divisible by 39, right? Or all multiples of 39. So it's really the same idea. It's 200 over 39. Take the floor function. 200 over 69. 200 over 299. And finally, for the triple intersection, it's divisible by 3, 13, and 23, right? These are all prime numbers. So now we're just subtracting floor function of 200 divided by 897. And notice here that these two terms are 0. This is 0 and this is 0, and that's fine. Right? It just means that there are no elements in that intersection. And then you can just compute this yourselves, right, to get the final answer here.